All right, hello everyone, and welcome to my channel. This is an educational channel. We look at theories of everything, ancient and modern, and today is our 505th video that we've done on Dewey B. Larson and his reciprocal system of theory. Now, if you would like a kind of a rundown of what Larson's theory is all about, you want to watch any of my first 474 videos on this subject, where I go into at least a little bit of detail, get you up to speed on Larson's reciprocal system of theory. For now, for today's video, I'm going to assume that you have some working knowledge. Today we are going to be reading from chapter 18 of Larson's book called Basic Properties of Matter. That's on chemistry. And we're reading from chapter 18 called The Retreat from Reality, which he goes into. This is more of a kind of a history of science part of the book, where he goes into the history of the black hole theory and how it is basically one assumption piled upon another, and that when you pile that many assumptions, there is pretty much no chance of the theory being correct. And I want to get right into it because we've got a lot of ground to cover here. So if you want to start at the beginning of this chapter, go back and listen to yesterday's episode, and we'll go from there. Okay. Here, we need to consider the status of assumptions in the structure of scientific theory. The construction of physical theory is a process of applying reasoning to premises derived initially from experience. Where the application involves going from the general to the particular, the process is deductive reasoning, which is a relatively straightforward operation. To go from the particular to the general requires the application of inductive reasoning. This is a two-step process. First, a hypothesis is formulated by any one of a number of means. Then the hypothesis is tested by developing its consequences and comparing them with empirical knowledge. Positive verification is difficult because of the great complexity of physical existence. It should be noted in this connection that agreement of the hypothesis with the observation that it was designed to fit does not constitute a verification. The hypothesis or its consequences must be shown to agree with other factual knowledge. Because of the verification difficulties, it has been found necessary to make use, at least temporarily, of many hypotheses whose verification is incomplete. However, a prominent feature of so-called modern physics is the extent to which the structure of theory rests on hypotheses that are entirely untested and, in many cases, untestable. Hypotheses that are accepted and utilized without verification are assumptions. The use of assumptions is a legitimate feature of theory or model construction, but in view of the substantial uncertainty as to their validity that always exists, the standard scientific practice is to avoid pyramiding them. One or two steps into the unknown are considered to be in order, but some consolidation of the exposed positions is normally regarded as essential before a further unsupported advance is undertaken. The reason for this can easily be seen if we consider the way in which the probability of validity is affected. Because of the complexity of physical existence mentioned earlier, the probability that an untestable assumption is valid is inherently low. In each case, there are many possibilities to be conceived and taken into account. If each assumption of this kind has an even chance, 50%, of being valid, there is some justification for using one such assumption in a theory, at least tentatively. If a second untestable assumption is introduced, the probability that both are valid becomes 1 in 4, and the use of these assumptions as a basis for further extension of theory is a highly questionable practice. If a third such assumption is added, the probability of validity is only 1 in 8, which explains why pyramiding assumptions is regarded as unsound. A consideration of the points brought out in the foregoing paragraphs puts the status of the nuclear theory into proper perspective. The 14 steps in the dark that we have identified in the path of development of the currently accepted atom model are totally unprecedented in physical science. The following comment by Abraham Pais is appropriate. Quote, "Despite much progress, Einstein's earlier complaint remains valid to this day," Einstein says the theories which have gradually been associated with what has been observed have led to an unbearable accumulation of individual assumptions. Of course, it is possible for an assumption to be upgraded to, this is Larson's words, of course it is possible for an assumption to be upgraded to the status of established knowledge by discovery of confirmatory evidence. This is what happened to the assumption as to the existence of atoms. But none of the 14 numbered assumptions identified in the preceding discussion has been similarly raised to a factual status. Indeed, some of them have lost ground over the years. For example, as noted earlier, the assumption that emission of certain particles from an atom during a decay process indicates that these particles existed in the atom before decay, assumption number 3, has been seriously weakened by the large increase in the number of new particles that are being emitted from atoms during high-energy processes. The present uncritical acceptance of the nuclear atom model is not a result of more empirical support, but of increasing familiarity together with the absence, until now, of plausible alternatives. A comment by N.R. Hansen on the quantum theory, one of the derivatives of the nuclear atom model, is equally applicable to the model itself. This theory, he says, is conceptually imperfect and riddled with inconsistencies. Nevertheless, it is accepted in current practice because, quote, "it is the only extant theory capable of dealing seriously with microphenomena," end quote. The existence or non-existence of alternatives has no bearing, however, on the question we are now examining, the question as to whether the nuclear atom model is a true representation of physical reality. Neither general acceptance nor long years of freedom from competition has any bearing on the validity of the model. Its probability of being correct depends on the probability that the 14 assumptions on which it rests are all individually valid. Even if no ad hoc assumptions were involved, this composite probability, the product of the individual probabilities, would be low because of the cumulative effect. This line of theoretical development is the kind of product that Einstein called, quote, "an unbearable accumulation of individual assumptions." Even if we assume the relatively high value of 90% for the probability of the validity of each individual assumption, the probability that the final result, the atom model, is correct would be less than 1 in 4. When the very low probability of the 4 purely ad hoc assumptions is taken into account, it is evident that the probability of the nuclear atom model, the atom of modern physics, being a correct representation of physical reality is close to 0. This conclusion, derived from an examination of the foundations of the currently accepted model, will no doubt be resisted and probably resented by those who are accustomed to the confident assertions in the scientific literature. But it is exactly what many of those who played leading roles in the development of the long list of assumptions leading to the present version of the nuclear theory have been telling us. These scientists know that the construction of the model in terms of electrons moving in orbits around a positively charged nucleus does not mean that such entities actually exist in an atom or behave in the manner specified in the theory. Erwin Schrödinger, for instance, emphasized that the model is, quote, only a mental help, a tool of thought, end quote, and is asserted that if the question, quote, do the electrons actually exist in these orbits within the atom, is asked, it is to be answered with a decisive no, end quote. Werner Heisenberg, another of the architects of the modern version of Bohr's atom model, tells us that the physicist's atom does not even, quote, exist objectively in the same sense as atoms or as stones or trees exist, end quote. It is, quote, in a way only a symbol, he says. These statements, applying specifically to the nuclear theory of the atom, that have been made by individuals who know the true status of the assumptions that entered into the construction of that theory, agree with the conclusions that we have reached on the basis of probability considerations. Thus, the confident statements that appear throughout the scientific literature asserting that the nature of the atomic structure is now known are wholly unwarranted. A hypothesis that is, quote, only a mental help is not a representation of reality. A theoretical line of development that culminates in nothing more than a symbol or a tool of thought is not an exploration of the real world. It is an excursion into the land of fantasy. The finding that the nuclear atom model rests on false premises does not necessarily invalidate the currently accepted mathematical relationships derived from it or suggested by it. This may appear contradictory as it applies that a wrong theory may lead to correct answers. However, the truth is that the conceptual and mathematical aspects of physical theories are, to a large extent, independent. As Feynman puts it, quote, every theoretical physicist who is any good knows 6 or 7 different theoretical representations for exactly the same physics, end quote. Such a physicist recognizes this many different conceptual explanations that agree with the mathematical relations. A major reason for this is that the mathematical relations are usually identified first, and an explanation in the form of a theory is developed later as an interpretation of the mathematics. As noted earlier, many such explanations are almost always possible in each case. In the course of the investigation on which this present work is based, this has been found to be true, even where the architects of present-day theory contend that, quote, there is no other way. Since the practical applications of a theory are primarily mathematical or quantitative, one might be led to ask, why do we want an explanation? Why not just use the mathematics without any concern as to their meaning? The answer is that while established mathematical relations may serve the specific purpose for which they were developed, they cannot be safely extrapolated beyond the ranges of conditions over which they have been tested, and they make no contribution toward an understanding of relations in other areas. On the contrary, they lead to wrong conclusions and constitute roadblocks in the way of identifying the correct principles and relations in related areas. This is what has happened as a result of the assumptions that were made in the course of developing the nuclear atom model. Once it was assumed that the atom is composed primarily of oppositely charged particles, and some valid mathematical relations were developed and expressed in terms of this concept, the prevailing tendency to accept mathematical agreement as proof of validity, together with the absence until now of any serious competition, elevated this product of multiple assumptions to the level of an accepted fact. Today, quote, today we know that the atom consists of a positively charged nucleus composed of protons and neutrons surrounded by negatively charged electrons, end quote. This positive statement or its equivalent can be found in almost every physics textbook. But any proposition that rests on assumptions is hypothesis, not knowledge. Classifying a model that rests upon more than a dozen independent assumptions, mostly untestable, and including several of the inherently dubious ad hoc variety, as knowledge, is a travesty on science. When the true status of the nuclear atom model is thus identified, it should be no surprise to find that the development of the theory of the universe of motion reveals that the atom actually has a totally different structure. We now find that it is not composed of individual particles, and in its normal state, it contains no electric charges. This new view of atomic structure was derived by deduction from postulates that define the universe of motion, and it therefore participates in the verification of the reciprocal system of theory as a whole. However, in view of the crucial position of the nuclear theory in conventional physics, it is advisable to make it clear that this currently accepted theory is almost certainly wrong on the basis of current physical knowledge, even without the additional evidence supplied by the present investigation, and that some of the physicists who were most active in the construction of the modern version of the nuclear model concede that it is not a true representation of physical reality. This is the primary purpose of the present chapter. In line with this objective, the most significant of the errors introduced into electric and magnetic theory by acceptance of this erroneous model of atomic structure have been identified in the preceding pages. But this is not the whole story. This product of, quote, an unbearable accumulation of individual assumptions has had an even more detrimental effect on astronomy. The errors that it has introduced into astronomical thought will be discussed in detail in Volume 3, but it will be appropriate at this time to point out why astronomy has been particularly vulnerable to an erroneous assumption of this nature. The magnitudes of the basic physical properties extend through a much wider range in the astronomical field than in the terrestrial environment. A question of great significance, therefore, in the study of astronomical phenomena is whether the physical laws and principles that apply under terrestrial conditions are also applicable under the extreme conditions to which many astronomical objects are subjected. Most scientists are convinced, largely on philosophical rather than scientific grounds, that the same physical laws do apply throughout the universe. The results obtained by development of the consequences of the postulates that define the universe of motion agree with this philosophical assumption. However, there is a general tendency to interpret this principle of universality of physical law as meaning that the laws that have been established as applicable to terrestrial conditions are applicable throughout the universe. This is something entirely different, and our findings do not support it. The error in this interpretation of the principle stems from the fact that most physical laws are valid in the form in which they are usually expressed, only within certain limits. Many of the currently accepted laws applicable to solids, for example, do not apply at temperatures above the melting points of the various material substances. The prevailing interpretation of the uniformity principle carries with it the unstated assumption that there are no such limits applicable to the currently accepted laws and principles other than those that are recognized in present-day practice. In view of the very narrow range of conditions through which these laws and principles have been tested, this assumption is clearly unjustified, and our findings now show that it is definitely incorrect. We find that while it is true that the same laws and principles are applicable throughout the universe, most of the basic laws are subject to certain modifications at critical magnitudes, which often exceed the limiting magnitudes experienced on Earth and are therefore unknown to present-day science. Unless a law is so stated that it provides for the existence and effects of these critical magnitudes, it is not applicable to the universe as a whole, however accurate it may be within the narrow terrestrial range of conditions. One property of matter that is subject to an unrecognized critical magnitude of this nature is density. In the absence of thermal motion, each type of material substance in the terrestrial environment has a density somewhere in the range of from 0.075 hydrogen to 22.5 osmium and iridium, relative to liquid water at 4 degrees centigrade as 1.00. The average density of the Earth is 5.5. Gases and liquids at lower densities can be compressed to this density range by application of sufficient pressure. Additional pressure then accomplishes some further increase in density, but the increase is relatively small and has a decreasing trend as the pressure rises. Even at the pressures of several million atmospheres reached in shockwave experiments, the density was only increased by a factor of about 2. Thus, the maximum density to which the contents of the Earth could be raised by application of pressure is not more than about 15. The density of most of the stars of the white dwarf class is between 100,000 and 1 million. There is no known way of getting from a density of 15 to a density of 100,000. And present-day physics has no general theory from which an answer to this problem can be deduced. So the physicists, already far from the solid ground of reality with their hypotheses based on an atom model that is only a symbol, plunge still farther into the realm of imagination by adding more assumptions to the sequence of the 14 included in the nuclear atom model. It is first assumed, number 15, that at some extremely high pressure, the hypothetical nuclear structure collapses, and its constituents are compressed into one mass, eliminating the vacant space in the original structure, and increasing the density in to the white dwarf range. How the pressure that is required to produce the collapse is generated has never been explained. The astronomers generally assume that this pressure is produced at the time when, according to another assumption, number 16, the star exhausts its fuel supply. With its fuel gone, the star can no longer generate the pressure needed to maintain itself against the crushing force of gravity. That's a quote. But fluid pressure is effective in all directions, down as well as up. If the crushing force of gravity is exerted against a gas rather than directly against the central atoms of the star, it is transmitted undiminished to those atoms. It follows that the pressure against the atoms is not altered by a change of physical state due to a decrease in temperature, except to the extent that the dimensions of the star may be altered. When it is realized that the contents of ordinary stars, those of the main sequence, are already in a condensed state, a point discussed in detail in Volume 3, it is evident that the change in dimensions is too small to be significant in this connection. The origin of the hypothetical crushing pressure thus remains unexplained. Having assumed the fuel supply exhausted and the star cooled down in order to produce the collapse, the theorists find it necessary to reheat the star, since the white dwarfs are relatively hot, as their name implies, rather than cold. So again, they call upon their imaginations and come up with a new assumption to take care of the problem. They assume, number 17, that when the atomic structure collapses, the matter of the star enters a new state. It becomes degenerate matter and acquires a new set of properties, among which is the ability to generate a new supply of energy to account for the observed temperature of the white dwarf stars. Even with the wide latitude for further assumptions that is available in this purely imaginary situation, the white dwarf hypothesis could not be extended sufficiently to encompass all of the observed types of extremely dense stars. To meet this problem, it was assumed, number 18, that the collapse which produces the white dwarf is limited to relatively small stars, so that the white dwarfs do not exceed a limiting mass of about 2 solar masses. Larger stars are assumed, number 19, to explode rather than merely collapse, and it is further assumed, number 20, that the pressure generated by such an explosion is sufficient to compress the residual matter to such a degree that the hypothetical constituents of the atoms are all reconverted into neutrons, producing a neutron star, currently identified with the observed objects known as pulsars. There is no evidence to support this assumption. The existence of a process that accomplishes such a conversion under pressure is itself an assumption, number 21. And the concept of a neutron star requires the further assumption, number 22, that neutrons can exist as stable independent particles under the assumed conditions. Although this is the currently orthodox explanation of the origin of the pulsars, it is viewed rather dubiously even by some of the astronomers. Martin Harwit, for instance, concedes that we have no theories that satisfactorily explain just how a massive star collapses to become a neutron star. That's a quote. Back to Larson. The neutron star, too, is assumed to have a limiting mass. It is assumed, number 23, that the compression due to the more powerful explosion of the larger star reduces the volume of the residual aggregate enough to enable its self-gravitation to continue the compression. It is then further assumed, number 24, that the reduction of the size of the aggregate eventually reaches the point where the gravitational force is so great that radiation cannot escape. What then exists is a black hole. While it is not generally recognized as such, the self-gravitation concept in application to atoms is another assumption, number 25. Observations show only that gravitation operates between atoms or independent particles. The hypothesis that it is also applicable within atoms is derived from Einstein's general theory of relativity. But since there is no proof of this theory, the points that have been thus far been adduced in its favor are merely evidence. This derivation does not alter the fact that the hypothesis of gravitation within atoms rests on an assumption. Most astronomers who attempt the existence of black holes apparently prefer to look upon these objects as the limiting state of physical existence, but others recognize that if self-gravitation is a reality, and if it is once initiated, there is nothing to stop it at an intermediate stage such as the black hole. These individuals therefore assume, number 26, that the contraction process continues until the material aggregate is reduced to a mere point, a singularity. This line of thought that we have followed from the physicist's concept of the nature of electricity to the nuclear model of atomic structure, and from there to the singularity, is a good example of the way in which unrestrained application of imagination and assumption in theory construction leads to ever-increasing levels of absurdity. In this case, from atomic collapse to degenerate matter to neutron star to black hole to singularity. Such demonstration that extension of a line of thought leads to an absurdity, the reductio ad absurdum, as it is called, is a recognized logical method of disproving the validity of the premises of that line of thought. The physicist who tells us that the laws of modern physics virtually demand that black holes exist is, in effect, telling us that there is something wrong with the laws of modern physics. In the preceding pages, we have shown just what is wrong. Too much of the foundation of conventional physical theory rests on untestable assumptions and models. The physical theory derived by development of the consequences of the postulates that define the universe of motion differs very radically from current thought in some areas, such as astronomy, electricity, and magnetism. Many scientists find it hard to believe that the investigators who constructed the currently accepted theories could have made so many mistakes. It should be emphasized, therefore, that the profusion of conflicts between present-day ideas and our findings does not indicate that the previous investigators have made a multitude of errors. What has happened is that they have made a few serious errors that have had a multitude of consequences. The astronomical theories based on the nuclear atom model that have been mentioned in this chapter provide a good example of how one basic error distorts the pattern of thinking over a wide area. In this case, an erroneous theory of the structure of the atom leads to an erroneous theory of extremely high density, which then results in the construction of erroneous theories of all of the astronomical objects composed of ultra-dense matter. Not only the white dwarfs, but also quasars, pulsars, X-ray emitters, and compact galactic cores. Once the pyramiding of assumptions begins, such spurious results are